Okay, so today we will talk about the number system, the mathematics behind the number system. Okay, so before we talk about more formally, I just would like to talk a little bit history of my number. So it's the number we use in day-to-day life, right? And it actually has been used mathematically since like 4000 BCE, like in the Sumerian civilization, like in Mesopotamia. They have used the numbers, they have used symbols to denote numbers. And later on, like in Babylonian civilization, and also we have a Roman civilization, we have seen the Roman numbers, right? So the humans use symbols to denote numbers. Okay. So this is we have seen this for a long time, but there is a change in the number representations. So previously we use we have a symbols which we just group them. If you recall the Roman numbers, so we know that there are symbols like 1 or 5 or 10, right? So these are like symbols to denote some small numbers, 1, 5, 10. And if you want to represent some other numbers, we use them we combine them, right? Suppose we want to use 3. So what we will do, we write 1 3 times, right? Suppose we want to use, say, 7. We write 5, and then we had 2 more. Okay, so that we know in the Roman system. So this is one kind of representation of a number. Okay, and there is one more that we use like denote the number, like decimal system, like to denote 7 as a 12, we write 1 and 2, right? So there is a basic difference between these two representations. The one is kind of you are adding whatever symbols you are using, and other one is you are not adding. This is not 3, right? This is 12. So there is a basic difference, and that changes in modern science. Like it was not there before. So the symbols that we use, like 1, 2, 3, 4, it was also long time back, but initially there was no 0 symbol. So the symbol 0 is introduced by Aryabhatta, but that was like a placeholder. That was not as a value. Okay, so suppose we want to represent 10, we use 1 and 0. That 0 here is just not like a value, it's just a placeholder. Okay, and later on Brahmagupta introduced 0 as a number. That was a huge change in the number system, and the negative numbers also, like the negative -1, -2, -3. And then we have like the modern representations like this. So you see the basic differences. Like these are like you are adding these numbers, but here you don't add as such. We have a different way to represent, or different way to find the actual value of this number. So for each place we have some value. Like this will be like 1 into 10 plus 2, right? So there are very basic differences. It used to be like this. And another fact I just want to mention, just for a history point of view, like it used to be grouping up to 60 in the long time back, like in Babylonian time or during that time, like we used to group like number 16. 60 is like 60 is like kind of they're like a base. Right now we are using 10, base 10, right? And computer uses base 2. So we have a different base, but why 60? 60 looks very odd, right? So what we think or believe that possibly there are 2 factors is coming. Like one factor is that 60 has several factors, like 2, 3, 4, 5, 6, lots of factors. 60, if you look at 60 numbers, you see many factors. And another fact is that the human observed that the total time it takes 1 day, and if it's close to the multiple of 60, so that we can divide, like 60 seconds is 1 minute, 60 minutes is 1 hour, like that. Okay. So also we measure the degree in that way, like 60 degree, and then 16 times 6 is 360 degrees. So total circular degree is 360, which is a multiple of 60. So 60 is becoming like a unit, more favorite choice at that point of time. But later on it becomes 10. That was very common. We don't use 60 base. Right now we use 10 base. And what was the reason for moving from 60 to 10? You have any idea? I can just pause. And anyone can tell, like, why you moved from 60 to 10? Like, what is the 10? What is about 10? Yeah, you can guess.
Maybe 10 is more favorable to them.
Yeah, it could be any number. Like, it could be 8 also. It could be 12 also. Like, why you choose 10? So actually any base is possible. The reason behind 10 is this finger. So we count like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we see the 10 numbers are there. And then if you want to, that's like an atomic thing we have. So that is the main reason to use 10 as a base. Okay. Okay, so we have some amount of history. Now let's go to the more actual mathematics of this number representation. So we know, like, there are natural numbers like 1, 2, 3, 4, so on. These are called the set of all natural numbers. Okay. In terms of the history, appears before very fast, because we just count things. There is nothing zero at that point of time. At zero things is not that we didn't feel that we should have a number 0 for something. So because whenever we count, we should have 1, 2, 3, 4. Even fractions is also not relevant at that point. So we have this set of natural numbers. Then, as I said, like the Brahmagupta introduced 0 and the negative numbers, right? So set of whole numbers, when we have a 0 is introduced, and set of integers will be all the negative numbers, including this, right? And then we can look at how we can plot these numbers. If we have some visual representations, it actually helps for better understanding. Like, these are numbers, we understand everything, all these numbers very well, but just let us see how we can represent these numbers. So we draw a line, and we just mark a point, we call it 0, and we just decide one distance. Let's say it's called 1, and afterwards same distance I will increase by 1, right? And if you go left, it will be minus, and so on, right? So these are the numbers in the line, okay? And if you want to, now if you see, there are lots of points within that line also. Like, we are having few points. What about inside? Like, okay, like if you just take the middle point, we get 1 by 2. So if we divide the numbers into small parts, what we get a fractions, and this is called set of all rational numbers, right? So set of all rational numbers will be like a by b, where b is not equal to 0, and both a and b are integers, right?
Yes.
We can have some reduced form, like, okay, we can assume that b is positive, b is natural number, a could be negative, and we can also take out the common factors out. So those type of reduced form of a fraction can be used, but there is no problem even if I write 3 by 6 instead of 1 by 2. That's okay. That's rational number. 3 by 6 is a rational number, which is same as 1 by 2. Okay, so these are this is the picture. And now if you see, like, there are lots of numbers. Like, say this is 3 by 2, right? This is 3 by 2, and in that way you can find different rational numbers. But now, even in this real line, that there are lots of rational numbers. There are infinitely many rational numbers, right? But still, there are some more points, right? And these are called irrational numbers, right? So you find, so we see that, okay, rational numbers are good. We can write down a fraction, but still we see there are some numbers which are not rational numbers. So how we observe that, like, why there are some numbers which are not rational?
Because they don't have any ending, like in decimal they repeat.
Yeah, so right now I haven't talked about the decimal, but just one simple numbers which is not rational. Can you tell me one number which is
Pi, which is 3.
pi? Is, you are saying something very definitely pi is irrational, but something very simple.
It could be 1.08, then 0.008.
No, so very simple is a root over 2. Root over 2 is a irrational number. Let us quickly check why it is so. Let us check. Let us prove that why root over 2 is irrational number. So we know what rational number is. Rational number is a fraction of integers. Okay. So how do we prove that root over 2 is irrational number? So what will be the approach? Like, okay, like if you want to prove that root over 2 is not rational, there are different proof strategies. Like, whenever we want to prove some theorem, sometimes we use induction for proving. Sometimes we use some other method. And there's one important method you have to understand, like, when we should apply. It's called proof by contradiction. So suppose you want to prove something, what you do, you assume that this is not true, okay, and then you find something which should not be true, which cannot be true. So that means where it goes wrong, it goes wrong in our initial assumption that we assume that my statement is not true. So here we will assume, suppose not, that root 2 is a rational number. Suppose not, so root 2 is a rational number then. So by definition of rational number, I know that root 2 should be m by n, right? That's what the rational number is defined. Like, you take two integers and divide, then you get rational number. Any rational number should be like this. Now what we will do, okay, so you have to understand what root 2 means. So root 2 is a number if you square it and you get 2. Okay, so if you square it, you should get 2. So that's what I have to use. So I have to square both sides. So by squaring both sides, what do we get? Like, just square both sides. We get 2 equal to m square by n square. And that shows that m square equal to 2 times n square. 2 times n square is now m and n are integers, right? So 2n square is a even number. Yes, right. So m square is an even number. Because m square is even, then m must be even. Because if you take any odd number and square it, it has to be odd number. So that forces that m is even, and we can write that m as, say, 2 times a, right? So just replace that back, then, okay, we get 2a whole square. Okay, so here I have to write one more thing. So I didn't write that I will use that m and n in a reduced form. I can always write a rational number such that both m and n are relatively prime, means there is no common factor, right? Or for my purpose, for this particular context, I can assume that both are not even. If both are even, I will divide by 2, right? And then I get a smaller form of the rational number. Even if after dividing by 2 both are even, then again I will divide it by 2, and I can continue until one of them become odds, and then I will stop. Okay, so here I can assume that, we can also assume that m and n both are not even. I mean, one of them can be even. Both simultaneously are not even.
Well, they are not co.
Yeah, so there can be a, here I don't need that they are co-prime or there is some common factor of that. There is no common factor of that. I don't need in my problem, but we can actually assume. That's safe to assume. Maybe some other problem we may need it, but this problem, what I need, that both cannot be even simultaneously, because I am getting even, like m becomes even. Okay, m becomes even. Okay, good. M can be even. There is no issue. N is not even, then is fine. But now if I replace m by 2a, what do I get is 2a whole square equal to 2n square. That means 4a square equal to 2n square. Just simplify, you get n square equal to 2a square. And I have a similar situation, what I had for m. Now n square equal to 2a square, so n square is even, n is even, and that cannot be possible. So that shows that both m and n are even, which actually contradicts our initial assumption, right? So that's the proof. Just what we write here, we write this symbol, this notation, the two arrows moving each other or directing each other. Okay, so this is a symbol for contradiction. That means something wrong happened, and something wrong happened in the assumption that I have written root 2 like this. That completes the proof that root 2 cannot be rational. Okay, it's just a quick exercise, maybe or homework, maybe not. You can try at home to show that. I think this one is easy. The first, there are two exercises. First one is easy, to show that root 3 is irrational. Yeah, actually, you can copy the same argument roughly. Just instead of 2, it will be like a 3, right? It's a multiple of 3, and so. But still, it's recommended to go through the same argument, whether you have any. There are some steps looks not similar, or something is different happening or not. So one must check that root 3 is irrational. But the interesting one is to prove that root 2 plus root 3, that is irrational. Okay, so here one can argue that, okay, maybe root 2 is irrational, we already know. Root 3 is also irrational. Okay, so we assume that we have proved it. So we add 2 irrational number. So maybe just adding 2 irrational number is an irrational number. Like if we add 2 rational number, we get rational number. So maybe we add 2 irrational number, we get irrational number. Is it true that if we add 2 irrational number, we always get irrational number?
Not always.
Not always. So that means, how do you, if someone makes a statement that sum of 2 irrational number is irrational number, so you are saying rightly that it is false. So how do you prove that this statement is false?
Basically, what we can do here is
not here, just the statement that sum of 2 irrational number is irrational number. Someone is saying that it is false. So what has to show for that?
we again could assume that it is a rational number.
No, you have to give a counter example. What you have to, if someone says that sum of 2 irrational number is irrational number, or suppose you say that sum of 2 irrational number is irrational number, I said no, and I can prove, or I can justify my claim that it's no by showing a counter example here. I have to show a counter example, right? So the counter example, one can, simple counter example, say 1, or maybe say little bit bigger, say 4 minus root 2 and root 2. We know root 2 is irrational number. 4 minus root 2 is also irrational number. That can be easily checked because again by contradiction, suppose it is a rational number, suppose not, suppose it is a rational number, then this is rational, so this is equal to a by b. Then just what I can write, like root 2 will be 4 minus a by b, right? And you can just simplify and get 4b minus a by b. So root 2 becomes rational number. So that's not possible, right? So 4 minus root 2 is a rational number. Root 2 is also a rational number. And if you add, you get a rational number. So just giving one counter example will be enough to refute a claim that sum of two irrational number is a irrational number, which is actually not true. So that argument cannot be used for this homework. To prove that root 2 plus root 3 is irrational, you have to somehow prove other way. Okay, so this is the homework. I just want to keep this as homework for everyone. Just try, and if you have any question on this, if you can ask me, we'll try to help. Okay, so we have a concept of the irrational number now. Now we have a real line, we have rational numbers, and whatever else is irrational numbers. Okay, there are some irrational numbers which are good and some are not. What do you mean by good? How do I say a irrational number is good? Okay, there is no such definition of good. There is no terminology good. I am saying just good. But there is some terminology called constructible irrational number. What it means is just again some history, like the Greek mathematicians, they're good in geometry. Right? So you see Euclid, Pythagoras, lots of Euclid, Greek mathematician who contributed a lot in geometry. So what they're looking for the numbers which can be constructed by using ruler and compass, whatever tools we usually have, right? We usually use the ruler and compass. Okay, so we can construct. First of all, you have a line and we fix a point, and let's call it 0 point, and fix a distance and let's call it 1, and then we can make a same distance and we can cut another point, we can call it 2, and so on. And similarly, if you do this way, so that means we can construct all integer. I mean, I can reach or I can mark integer points by using ruler and compass. Just initially you have to fix 0 and 1. We can call arbitrary some point 0 and some point 1, and then you are all the integers are ready. Okay. Okay, so how about rational number? Can I construct rational numbers? How about how construct a half? Half is actually easy, so there are constructions for bisection, right? But if I want to construct 1/3 or 1/5, 1/4 will be easy again. So 1/3, 1/5, how we can construct? So okay, so we see that it still can be constructed. Just draw a line again and pick any distance, some point, and an equal distance you pick 3 points. Okay, and then you join these 2 points. So we already have like a 1/3 of this. This interval, this length is a 1/3 of whole. I can always make a equal copies, whatever the length is, by just using the ruler, or the compass without drawing the circle. I just take this segment and put it the center there and draw another circle with same radius. You get a equal distance point, right? The same way we will draw 2, 3, 4, and so on. Okay, and then we will construct parallel line to this, and wherever it will cut will be like a 1/3, 2/3, and 1, right? And that you can do same thing for 1/5 or 1/6, 1/7, whatever fractions, and even for 2/5, 2/5, 3/5. Just you already have all these fractions. So what we have seen here, that rational numbers are constructible. Okay, and then we have Pythagoras. We know Pythagoras theorem. So we have this distance, and then we draw perpendicular and same distance 1, and just draw this hypotenuse. Like, let's call it, say, this is O, maybe this is A, this is B. Okay, so this hypotenuse, length of the hypotenuse by using Pythagoras theorem will be something, let's call it x. So Pythagoras says that x square should be equal to 1 square plus 1 square, which is 2. So x is some numbers which square is 2. So if I now just use the compass and just take a take O as a center and draw a circle, it will cut somewhere here, and let's call it the point P. And now if you want to measure this length OP is same as OB, and that is some number whose square is 2, and we can call it that square root of 2. Okay? So square root of 2 is also constructible. Okay. So in that way, we construct different numbers which are not even rationals. Square root of 2 is not rational, right? We can construct square root of 3 also. That will be again nice exercise, how to construct square root of 3. That's more like a geometric problem than number theory problem or number system problem. But just for because we also have to learn geometry, so that's like a related problem, like how you can construct square root of 3, like we have done for square root of 2. Okay, you have to use anyway Pythagoras theorem in a nice way. Okay, so we can construct square root of 2, square root of 3, square root of 5, any square root of any number, and then the mathematician community thought maybe we can construct all numbers by using ruler and compass. But there is a French mathematician, very famous mathematician, whose name is Galois. He proved that no, you cannot construct all numbers by using ruler and compass. So that's advanced algebra. I will not go. You will study, if you study mathematics in maybe undergrad or in grad course in algebra, you will study that. What I'm just saying, very few numbers so that to get a feeling that which are not constructible. For example, the cube root of 2, say, that you cannot construct. You may have heard that, okay, can I trisect an angle? That's not possible. That's not a, I'm not saying in terms of the number, because the trisection angle is kind of asking for some task. But here, as a more precise example, will be cube root of 2 or cube root of any numbers will not be constructible. So that's an example, and there are many examples. So Galois actually characterized like what are the all numbers you can actually construct by using ruler and compass. Okay, so that means there are many numbers which are not constructible. Of course, this type of number like E, which appears in geometry, pi appears in geometry, E appears in calculus, they are not rational numbers and they are not constructible. Okay. But this number, there is a basic difference. These numbers is something called algebraic numbers. So what is transcendental number? This number you can write. For example, if you call this as a, say, some x, then you can write x cubed minus 2 equal to 0. For E or pi, you don't have any such relation. Like pi is maybe pi cube minus 2 pi plus 3 equal to 0. No. Or find any polynomial relations over pi, it won't be 0. So if some numbers has some polynomial relations or becomes root of a polynomials, then we will call those number algebraic number, and if it is not, then we will call it transcendental. So pi and E are those are transcendental. So those are very difficult numbers, very difficult to understand how what what these numbers are, how they behave. So we usually will not study that much. Mostly we'll consider the rational numbers, or sometimes some kind of simple algebraic number like square root of 2, cube root of 2. Some of them may not be constructible, that's a geometry point of view, but those numbers are still interesting for us. Okay. Okay, so we get some idea about the numbers, and we try to represent some numbers by using geometry, lines, rules and compass, ruler and compass. But that of course is not a good way to write a numbers, represent a number. So what we use the base system. Okay, so as I was saying in the beginning, like we have a history, like we have one way to represent a number as a grouping, and another is the base representation. So let us see what base representation means. So base representation of a number. Of actually any real number, but right now I'm writing number or integer or positive integer, but we can actually do it for any real number. Okay, so that's like a decimal point representations we can use. But for the time being, let's see simple integer or positive integers. Okay, so what we will do to just to distinguish from the multiplication notations, like if we write 2, 3, so when I write x, y, it means x times y, right? When I write 2, 3, does it mean 2 times 3 or it represents 23? Okay, but when I want to use as a variable, okay, I want to use, okay, 2-digit number, maybe I will write, okay, x, y is a 2-digit number, but then there will be confusion. X, y is a 2-digit number. Is it a x times y you are saying, or x in 10th place, y is a unit place is a 2-digit number? So that we have to make clear, and that's why we have our different notations. We will use different notations. So we will write like say let's take up some 5-digit numbers. Say. So 5-digit number like say A5, A4. Maybe we start from okay. So let's start A0 at the unit place, A1, A2, A3, A4. Okay, that's a 5-digit number. But it's not a multiplications. Just to denote that it is not a multiplications, we just write a bracket and we put 10 here. Okay, so it's saying two things. This bracket is saying, okay, just treat it as a different thing, like we have written something here also. So it's not a multiplications, it's a base 10 representation of a number. So A0, A1, A2, A3, A4, all these values will be integer between, actually non-negative integer between 0 and 9 for base 10, right? So AIs are integers between 0 and 9. Okay, so this will be some number, and what this n will be. So we know like these are like a place value, face value, like AIs, but there is a place value, right? So A0 has a place value A0, A1 has a place value 10 times A1, and so on, right? And if you add all of this, then you get n. So n is basically 10 to the power 4 A4. Okay. Okay, so this is a representation of a number, of a natural number. If you want to use a negative, if you want to represent negative number, so we put a negative minus sign. Okay, so this is fine. This we all know, but this representation actually is important in the sense like whenever you see some problems with which involves representations, digits. For example, we know, all of we know from school days that whether a number is divisible by 9 or not, or divisible by 11 or not, we look at the decimals. We look at the digits, right? The decimal. We first look at the decimal representation of the number and look at the digits, and we do some calculations on those digits, and then we, for example, to check whether the number is divisible by 9, what we do is we just sum all the digits, right? And then we look at whether this sum is divisible by 9 or not. And if it's divisible by 9, then we say the number is divisible by 9, otherwise not. But that's, we all know, like we know some tricks for how to check some number is divisible by 11 or not, or even 5 or not, 6 or not, like that, right? Or sometimes people are looking for, excited to see, is there any rule for 7 or 13? There is no good rule, but okay, still we can find some rule. But to prove why this rule works, we have to have this representation. We have to know what a number means. This number, a number means in this. Unless we don't have this actual absolute value, the actual value of the number in terms of the digit, you cannot prove whatever you are claiming. So as a statement is good, but if you want to prove, we need this. Okay. Okay, so this is fine. Let's see some applications of this type of representation. Okay, so one applications I taught last time. Applications means some results or some theorems or some tools where I need this base representation. Okay, so I don't know whether you remember this puzzle or not. Like I asked you to think two numbers between 0 and 9. Okay, so now we can quickly do this puzzle or this magic. So just think two numbers between 0 and 9. Okay, and you pick the first number and double it, and then you add 5. And then you multiply by 5. Okay, after you multiply by 5, you have the other number you haven't used so far. You add that number, and then you tell me this final sum. Once you add this, what do you get? So you get 62. So what you thought, you got 3 and 7. So what is the logic behind this? Is actually simple. You can use this logic. The method or behind to find these numbers is simple, but at the same time I can actually say why this works. So first number is x. So first I ask to double it. So you got 2x. Then what I ask to add 5, right? And then I ask to multiply that by 5 again, right? And then I ask at the other number. So if you simplify this, what do you get? And you said this number is 62, right? So I have this equation. I don't know x and y, but I know this equation. Okay, that implies 10x plus y equal to 37, right? So you just subtract 25, I get 37. And that tells you that x is 3 and y is 2. Sorry, y is 7. Right? Yeah. Okay, so here I use actually this is the representations, and there is one more thing, that for every n there exists a unique representation. There is a unique such representation. Okay, so this exclamation means unique. That means the same number I cannot write in two ways. Okay, given that AIs are between 0 and 9, so if you use one of the, if you think one of the number more than 10 or more than 9, even 10 or 11, then that trick will not work. So that's why I said two small numbers between 0 and 9. And also they have to be integers. If you just thought maybe 2.5, 3.5, then also it will not work. Okay, so they are integers, and then we have unique representations if they are between 0 and 9. That is the kind of a results behind the base representation we need. And then we have this like x3 and y7, and this is definitely one representations, one solid representation, and this is a unique representation. There cannot be any other x and y for which this is true. Okay, so that shows that by uniqueness, this is by uniqueness. The last implications that from here, how we can say x equal to 3, y equal to 7? Of course, x equal to 3, y equal to 7 is one answer. But how I can know that you have actually thought 3 and 7, maybe 4 and 2 or something else? No. The 37 can be written uniquely by in the form 10x plus y, where x and y are between 0 and 9. Okay. Okay, so this is one applications. Now if you go to another one. Okay, so let's do one more thing. So just write one number, 3-digit number. Okay, some 3-digit number, and then you write side by side. So you can do your one. So I am doing my one. Like I took say 1, 3, 4, and then I write 1, 3, 4 again. What I got a 6-digit number, little big number. Okay. Now I will divide this number by 7. Okay. I need some space. Three-digit number we ought to understand. So yeah, pen is there. So just divide by 7. You get the. Are you getting any remainder? No, I am not getting any remainder. I'm lucky. Are you getting any remainder? We're also not getting remainder. Okay, good. So you got some quotient, right? And you divide it by 11. Let me divide my number. Oh, good. Are you getting any remainder? Oh, same here. I'm also not getting any remainder. Good. So far, so good. Now we got a little bit smaller number compared to the original number. You have divided by 7 and 11. So let us divide it by 13. Just divide. I will not do that.
Not getting any reminders.
And what is the quotient? It is? What is the original number?
100.
Yeah. So originally you thought 100 and you did all these steps, you got back 100. For me, it will be 134. So why it's happening? You can use this as a trick, a magic trick. You can frame this idea to how to stage this idea, that you can do it by your own way. But basic idea is, if you take any 3-digit number, if you write it down side by side, you get a 6-digit number, and then you divide by 7, 11, 13, one by one. No remainder will be there, first of all, and most importantly, last quotient, you will be same 3-digit number you have started with. The question is why? Why do we get back same number? The answer is behind this representation, base representation. But in a little bit different way you have to see. So this 6-digit number, 134134 in my case, okay, can be written as, so maybe I write like this. So if you just look at this 134, this number, let's call it x. Okay, so this x, whatever this number, is actually multiplied by 1000, and then we add this x. So this is my x and this is my x. So it's basically nothing but 1001 times x. So whatever number you actually wrote here is the 1001 times the number x. Okay. So what I ask you, multiply by 1001. Okay. In a nice way. Okay. Don't multiply by 1001. You just write the same 3-digit number side by side. Same as multiplying by 1001. And then what I ask, divide by 7, 11, 13. Okay. What about 7 times 11 times 13? That is actually 1001. So I am actually doing very silly things. I'm asking you multiply by 1001 and then divide it by 1001. Okay, we all know that, okay, multiply by 1001, divide by 1001, you must get back same number. What that is very obvious. But the interesting thing is that we are writing the same thing, we are doing the same thing in a different way. It's not clear in the beginning, but actually once you understand like what is happening here, then you see, yeah, basically we are multiplying by 1001 and dividing by 1001, but slowly. Okay, so this is one application, say like for base. Okay, so now I will talk about little more interesting applications. Okay, so you take any 2-digit number and square it. We're done. I think you have taken small, but very simple number. Just can you tell me what is your square number? Yeah, so okay, don't take that. Take something bad. What I will do basically, so okay, let me say what I'm going to do, then it will be easier for you. I will find out the square root of number. It's not difficult. We know how to find the square root of number, but I will find it quickly. Not like Shakuntala Devi, like she was like human computer, but I have some trick. I can apply some trick and which I can prove mathematically why the trick works again. So I'm just not happy with just say learning tricks, methods, showing magic. I am more fond of learning why it works. What is the reason behind that? I just want to know that much more. Definitely the method gives some fun, right? So we don't want to miss that fun also. But anyway, so give me a square numbers which is doesn't look so obvious, and I will find out the square root of that number as fast as possible.
49.
49 is 7. That's very simple. Okay. So give me a square number of a 2-digit number. 289, right? Okay. So your number is 17. I mean, square root is 17. Okay. Maybe another. If you have a calculator, you don't have the calculator. Okay. Yeah. If you have a calculator, you could have quickly take 2-digit number and square it. Maybe you can use my one if you want. Oh, where is the calculator? Yeah. Just there is a square here. Square and cube. So just take any 2-digit number and press the square thing. There's one is square, one is cube.
2401.
Oh, the big one. Okay, so now this one will be just a minute. I'm not as Kokantara Devi, so it's like 49. Okay, right? Good. And not only that, actually I can tell you the cube also. So if you just take a number and cube it, 2-digit number and cube it.
12,167.
12,167. Okay, so I just to remember something. Okay. Yeah, this is easy. This 23, right? So this is cube root. Okay, so we have seen something. So now maybe we can look for what method I am actually using and why this method works. Okay, both you have to understand. Okay, so let me first explain what is the method I am using. That's easy to explain, and then we will justify why it is true. Okay, so first of all, we know that these are perfect square numbers. So for the square number things, okay, I will do the same thing for the cube root number. So if we know that these are perfect square numbers, okay, so that we have to use. So that actually will help me to find the last digit. Like here, the 9 is the last digit of the square number. Here, 1 is the last digit of the square number, right? So if you square a number, the last digit of the square number actually depends on the last digit of your number, right? It doesn't depend on 1, it depends on 7. That actually tells you is 9, right? But there is another choice for last digit. That's 3 also gives a square. 1, 2, 3, 4, 5 always will give 5, 6, 7, 8, 9. So 1 and 9 will give 1 always. 2 and 8 will give 4. 3 and 7 will give 9. And 4 and 6 will give 6. Right? So by looking at the last digit, whether it's a 1, 4, 6, 9, you can tell whether the last digit is, but there are two options. So there is a one thing that if it is, say here is a 9, it could be the last digit could be 3 or it could be 7. Okay, so at least I know it is either 3 or 7. But which one it is, that I have to identify. And moreover, I have to identify the first digit also. Okay, so for that, now we'll just take out this 2-digit number. What is left is 2. Same thing for here, 2-digit number. What is left is 24. Okay. Here, I have to look for say for I'll do the same thing for both. Just explaining the method for the first one. So search for a number x such that if you just add 1, x into x plus 1 will be greater than equal to 2. Sorry, just a minute. I'm actually sorry, I'm wrong. But not greater than equal to that. I will do the next step. So search for a number x such that x square is less than equal to 2. Okay. So what I said actually next step. First I will do this is a step 2 maybe. The first step is to identify the two choices of the last digit. Last digits. Okay. And step 2, identify the to guess the first digit, and that guess is actually easy. Okay. So find out the largest x for which x square is greater than or equal to 2. So find the largest x. So here the largest x is 1 because 2 becomes 4, 2 square is 4. Here the last is 4, right? 4 square is 16, 5 square is 25, it's bigger. Okay. So the largest x is for both we will find. So that actually x will be your best the 10th place. X will be a 10th place digit. Okay. Good. Now we have to figure out which one in step 1 I have to choose. Okay. So whether it's 7 or 3. For that, I have to do this step 3. That okay, we already got x. Here x is what? 1, right? So 1 times 2. I compute 1 times 2. So first I compute x square, x times x. Now I compute x times x plus 1, little bit bigger. Okay. So x square is less than or equal to 2, I know, but x into x plus 1 is greater than or equal to 2. I will try to check that. If x into x plus 1 is greater than or equal to 2, then I will go for the higher number, the 7. Otherwise, I will go for the lower number, 3. Right? In here, what happens? Like in both cases, actually is greater than or equal to, like here, what I have? Sorry, it's like 4 into. No, sorry, I'm making some mistake, right? This is not 49. It should be 41 or no, but my method says it should be 41. So what I was saying, according to, if you just follow the blindly, so this will be like just take 4, okay, and then 4 into 5. 4 into 5 is less than equal to 24. Not less than equal, less than 24. So we have to take the smaller one. What is going on? No, I have to see this. Maybe I will resolve this maybe next class. This maybe I'm doing the step 3 wrong. Four into 5 is 20. Okay, let me see the proof. I remember how the proof works. So then we will actually able to identify where I went wrong. Okay, let's see the proof. What happened? Okay, so we have a 2-digit number. Okay, so let's say A and B. That is my n. And the n square is what? N square is okay. N is like 10a plus b. That is what base representations, right? And we look at the square. you have 100 square plus 20 AB plus B square. Okay? Okay. So what I am now doing, okay, so I'm asking whether B, okay, so first of all, this number is less than, strictly less than, B is, A and B is less than 10, between 0 and 9. So if B is less than 10, so this becomes what? 200A, right? So if you replace B by 10, so this becomes 200A. So I can take 100 common, and this A square plus 2A plus B square. Here I use the fact that B is less than 10. Why I am writing this? Because now it's like 100 times something. Okay, so 100 times something plus B square. Okay, now this is again less than 100 times A plus 1 whole square plus B square. Okay, so the n square is given to me. So if you write the n square, I just am looking into two parts. One part is the first two-digit number, sorry, last two-digit numbers, and another part is the first two-digit numbers. Okay, so let's call it, this is x and y. Okay, this is my n square. Okay, it's actually base 100. You can say it's like a base 100. I am writing. Okay, so this will be like 100x plus y. That number is given to me. Okay, so but we know capital X, and that capital X is actually greater than a square, greater than equal to a square. Yeah, capital X would be greater than equal to a square, but at the same time it is less than a plus 1 whole square. Okay, so that actually will help you to find A by looking at X. So that's what I did. Like, okay, so if you remember the number, it was say 289. So 289, this is capital Y and this is capital X. So capital X is 2. So I'm looking for number A whose square is less than 2, less than equal to 2. And if you just add one more, it becomes greater than 2. So 1 is that number. Okay, so in that way I can get A. By looking at this, I get A. So that part is easy actually, but the resolving the which one I will choose, because from Y I can know that it will be either 7 or 3. Okay, the B will be either 7 or 3, not the Y. So B will be either 7 or 3. But here what I thought it should be like, okay, we know that B is, what I have to decide whether B is greater than 5 or less than 5. That's what we have to decide. If I decide whether greater than 5, because if you see in the last picture, like we have like 3 and 7 give the same number 9. So one is less than 5, another is greater than 5. So one of the number less than 5, which gives the same digit with another number greater than 5. Basically, sum will be 10, like 1, 9, 10, 2, 8, 10. For 5, it will be always 5. 5 is the easy one, just you know it will be 5. Okay, so I have to find out this. Then I know whether 7 or 3. For this, okay, I go back again here and I replace, suppose B is less than 5. Okay, then this term will be less than 5, so it will be 100A, right? So 100 times A square plus A. 100 times A times A plus 1. And that's what I was actually doing, that if A times A plus 1, which is 1 times 2, is less than the number x, which is not means strictly less than. I need a strictly less than because you are strictly less than, which is not true. That's why it must be the other one. So if b is less than 5, then a into a plus 1 should be. So what I am, if b less than 5 should imply a times a plus 1 should be less than x. And b is greater than 5 imply a times a plus 1 should be greater than equal to x. But I don't know why it's not working here. For 24, I'm thinking so okay, maybe you have to see like what is going on here. Okay, so let's keep it for homework. We'll come to the next class. We'll come to this, like what is happening here. Like, so we got the idea, like we know like a, how to get the a and what are the two options of b. That's obvious. So that's what we have actually observed. But the only difficulty part remains like how to resolve the two cases, whether less than 5 or greater than 5. Okay. Okay. For the cube root, actually is easier. Actually, we do the same thing. For cube root, so we have a we divide into 3 parts. Like, so 2 parts, but 3 digits. So this is a 3 digit. This may not be 3 digit, but most of the times it might be 3 digits. Now it's like a base 1000. You can think of like a base 1000. Same as like, so this is the cube of the number AB base 10. So this will be given to you, right? And your goal is to find this A and B. That is the problem, right? Similar for the square root of problems. Okay, for that, what you need to have a you need to recall this cube of 1 digit. That might, if you do it for several times, then you will remember that. So like 1 cube is 1, 2 cube is 8. These are simple. 3 cube is 27. 4 cube is 64. 5 cube is 125. Yeah, after that I don't remember. 6 cube is 216. 7 cube is 343. 8 cube is 512, and 9 cube is 729. Okay. Yeah. So suppose I take some number, say 704969. And I want to find the cube root of this. So this is my y, this is my x. Okay. Okay, so what we know that if you just write down this cube, the 10a plus b whole cube. Previously we did the square, now we do the cube. So we get like 1000 a cube. So we know the a plus b whole cube formula, right? And then we have how much? Maybe we can write the 3ab, like 30ab. Sorry, 10a plus b, right? That will be 10a, right? And then we have a b cube. Okay. Now you can first of all, the first step is actually same. Like the last digit of 9 will actually depend on the last digit of y, which is 9, will actually depend on b. Doesn't depend on a, because you can check that b cube actually will give your, the last digit of b cube will be your 9. Now here, unlike the square root problem, here all are unique. That's a good thing. For the square root problem, the two things are going to the same. You have to resolve the case, and that was the hard case. We have got stuck there, but here there is no issue here, right? So here we actually have to actually can find one such number for 9. Okay, for 9 we have a 9, right? So then b is equal to 9. Okay, and then here you can use the same argument like what we did, like just replace b at most 10. So b can be at most 10. So if you place b at most 10, what do you get is 1000, sorry, strictly less than 1000 a cube plus b is 10, so 300 a plus b is 10, so 10 a plus 10 b, so 10 a plus 10. Okay, so a plus 1 times 10. So basically this will be, you just take 1000 common, a cube plus 3a square plus 3a, you can see this will come, and this is again strictly less than 1000 times a plus 1 whole cube plus b cube. Okay, so that says that the x should be less than a plus 1 whole cube, and it also should be greater than a cube. So that actually help you to find a. So if you remember this chart, so here is 704. So 704 is lying here. 704 is lying, so a should be 8. Okay, so this will give that a is 8 and b is 9 by looking at the last digit. So 89 is the answer here. So cube root of this will be 89. Okay, so cube root is actually easier to find compared to square root because I need 2 steps. The last steps is not required for the cube root. That's the good thing here. But on the other hand, you have to remember this cube. That so if you do this, if you can remembering the if you can remember this all these cubes, then you can do it very fast. Okay, but methods are both the same. Okay, so this is some applications we've seen regarding these base representations. Now we can okay, so now we just have few minutes left, so we can talk about the decimal representations. The point for the fraction, like how do you represent a fraction? Okay, so far we have represent the integer. Okay, now for fraction we have a decimal representation, right? The point, like we can write this like we have a say 2, 3.745 like this. Okay, so here it will be like a same thing, but you have to, instead of like a 1, 10, 10 square, you have a divided by 10, 10, 1, 10, 10 square like that. Like this will be what? This will be equal to 23. Okay, we know like, okay, so we should strictly follow the base representation things. Like it will be 2 times 10 plus 3 up to this point is okay. Then 0.75, 745, it will be like 7 by 10. Like the base value for 0.7 is 7 by 10. Instead of multiplying by 10, now you're dividing by 10. Then 4 by 100, I mean 10 square, plus 5 by 100, 10 cube, 1000. Right? So that is what, if you represent a fraction number, or like you use the decimal point. Right? So, okay, so this is, one thing is clear, that if you write like this, okay, this must be a, if we can actually write this like this, right? 23745 by how much? 1000. Right? So what is this? This is a rational number. Okay. So if you take any finite representation, finite means you stop after some point, it must be a rational number. Right? There is another representations. Sorry, there are another numbers where it doesn't stop, right? So this is finite. Suppose it is something like this, 223.999, or maybe use something else instead of 9. 23 point say 3. It's like a recurring decimals. This is called recurring decimal. So this is an infinite representations, not unlike the previously it was finite, but now it is infinite representation. What happens to this? Is it a irrational number or rational number? So we have a notation, shorthand notation for this. We write 2.3, you can just put bar or sometimes put dot. This is also rational number. Okay. For this, we have to use a geometric sum. Okay, like this is, if you just follow the definitions, it is say that 3 by 10. Okay, forget this 23 part. 3 by 10 plus 3 by 10 square plus 3 by 10 cube, so on. So we can take 3 by 10 common. We get 1 plus 3 by 10 plus 3 by 10. Sorry, not 3 by 10. 1 by 10, right? We take only 3 by 10 common. 1 by 10 square, right? So this is called infinite geometric sum. Like there is some note. If you write this infinite sum, this can be simplified as 1 by 1 minus r. Okay, you can remember this without the proof, but there is a proof for that. Actually, one can compute up to some r power n, but n can be as large as possible. Then kind of a limit concept can be used to prove that this is 1 by 1 minus r. So here we have a r is 1 by 10, right? So this sum will be 1 by 1 minus 1 by 10. So if you simplify this, what do we get? 10 minus 1 is 9, 10 will come on top, but there is a 10. So 3 by 10 times 10 by 9. So what do we get is a fraction 1 by 3. This part 0.3333. So in fact, you can show that for any recurring decimal, may not start from here. So a general recurring decimal could be like this, like say 0.374545. So 45 is repeating. So I can, this will be again a fraction. Okay. So you can actually again use this idea, just write a geometric sum. So actually you can, if you know, this can be written as like, okay, so 0.37 we know, okay, we just write 37 by 100, right? And for this, we have to write 45 by, I think, 9900, something like that. The 2 zeros because of this 0.37 and 99 will be because of the 2 places are there. So there is general formula. You can actually write it down and get a fraction out of this. But why this is coming? You can use this geometric sum to actually establish why it is why this expression is coming. So just write this 454545 indefinitely and use these expansions, the decimal representation things, and then you have a nice geometric sum. Then you can simplify using this formula. You will get this. Okay. So here is an interesting fact that I will not prove. Like what we have shown here, we have shown a finite decimal point representation, or infinite recurring decimal are rational numbers. That we have shown. They're eventually rational numbers. Okay. Okay. But the fact is that these are the only rational numbers. There are no other rational numbers. Okay. So the converse is also true. By converse, what you mean? If you take any representation which is not of the form, that means it is an infinite decimal, of course, and no repeating, then it cannot be rational number. It has to be rational number. So this converse is also true. That's the fact. It's not easy, but one can try to prove that why the converse is true. So one way to prove that every rational number can be written as either finite decimal representation or infinite recurring representation. Okay, what I've shown the other way. If you start with a number which has a finite decimal representations or an infinite or that's recurring representations, infinite recurring representations, then by using these geometric sum things, you can prove that number is essentially a rational number. Okay, but what I'm claiming right now is the other way, that if you take any rational number, that also of this form. Okay, so proving, if you want to prove this, you must try in this way, that okay, look at any rational numbers and then try to identify what is the decimal representations. That will be the right way to prove. But if you look at the other interpretation of this same statement, which says that if you take an infinite decimal representation number where these digits are not coming in a repeating ways, right? It's like a kind of coming arbitrarily. So if you look at the digits of pi, like pi 3.1417, something like that is an infinite sequence where you cannot predict like what will be the next digit. So it's coming in like a non-periodic way, aperiodic way. Like there is no period, or there is no repeating objects, that repeating structures is visible. So if you consider this type of infinite sequence of some numbers with that infinite sequence, that number has to be a rational number. So if you think in that way, it looks more difficult to prove, like okay, to prove something irrational. But when you want to prove this, you prove in that way. Okay, so this is the fact. Okay, so today we basically looked into the best representation of a number, both the rational numbers, also the integers. Okay, base 10, but the same thing we actually can do for base 2, because the base 2 is popular in computer. Computer uses base 2, because for base 2 what happens, just to give an idea like what is happening for the base 2, what we have done for base 10 so for today. But the same thing we can do if all these things can be done for any base, in particular base 2. The good thing is the base 2 is that the digits you will be using for base 2 is only two choices, either 0 or 1, because as I said, for the number integers, like for base 10 is between 0 and 9, right? So you have 10 choices for base 10, so 2 choices for base 2, and we can use only 0 and 1. Okay, and 0 and 1 are very nice number, like very small and nice numbers, right? We can think we can work on 0 and 1 very fast compared to other numbers. Okay, so that's why the base 2 is interesting, and we will also look into that base also in addition to base 10. Okay, so in the next class we will talk about the base 2 things. Next class we will talk about base 2 representations, some idea about what is happening, what is a good thing in the base 2, and also the divisibility of numbers. We go to the divisibility of integers. So far we just talk about the numbers, base representations, but now if you go by divisibility, like we didn't see like why a number is divisible by 9 by just looking at the sum of the digits is divisible by 9. We also know the trick for 11. All the tricks, like what are the tricks, like how what are the tricks for different divisibilities and why these tricks are working. So to establish those tricks, we have to study the divisibility of numbers. Okay, so maybe we will first talk about the divisibility and then we can go to the base 2. We will see like so these two are the important things we will study in the next class. Okay. Okay, so you have any questions? This I will stop. Okay, so I think that's all for today. Maybe we'll see next class.